One of the most persistent questions in astrobiology and cosmology is whether intelligent life exists elsewhere in the universe. The observable universe contains hundreds of billions of galaxies, each with hundreds of billions of stars. A significant fraction of those stars host planetary systems. Observations from missions such as Kepler have demonstrated that Earth-sized planets in habitable zones are common rather than rare. From a statistical standpoint, the emergence of life elsewhere is a plausible hypothesis. However, the existence of extraterrestrial life is distinct from the feasibility of interstellar contact. Distances between stars are measured in light years, making travel extraordinarily time-intensive, even at extreme velocities. More critically, the laws of relativity establish that no object with mass can reach or exceed the speed of light. As velocity approaches this limit, energy requirements increase without bound. Under known physics, intelligent life elsewhere remains possible. Routine interstellar travel does not. The universe is built at a scale that breaks human intuition. On a clear night, away from city lights, the stars look close. They look like objects suspended just overhead, near enough that the idea of reaching them feels like a matter of effort rather than impossibility. Two stars sitting side by side in the sky appear almost neighborly, as if you could draw a straight line between them and call it a short trip. This is the most persistent and dangerous illusion the universe produces. It is a lie told by distance itself, and it has quietly distorted almost every casual conversation ever held about alien visitors. The human visual system was not built for cosmic scale. It evolved to judge the distance to a predator, estimate the width of a river, track the arc of a thrown spear. The farthest our ancestors ever needed to perceive with any accuracy was the horizon, perhaps a few dozen miles on a clear day from high ground. Nothing in the evolutionary history of human perception prepared us to look at a point of light in the sky and intuitively understand that it sits 25 trillion miles away. So our brains do what they always do when confronted with something beyond their calibration range. They simplify, they compress, they make the incomprehensible look manageable. And the night sky, that flat dome of twinkling dots, is the most extreme version of this compression that nature has ever placed in front of us. Start with the nearest star system. Alpha Centauri sits 4.24 light-years from Earth. That number sounds almost modest. You can say it in under a second. But a light-year is not a human unit of measurement. It is an astronomical abstraction that takes an already incomprehensible speed, the speed of light at 670 million miles per hour, and multiplies it by an entire year of continuous travel. 1 light-year equals approximately 5.88 trillion miles. Multiply that by 4.24, and Alpha Centauri sits roughly 25 trillion miles from where you are sitting right now. To feel what that number actually means, try this. Start counting to 25 trillion at one number per second. Never sleep, never eat, never pause. You would need just under 800,000 years to finish. You would begin counting before anatomically modern humans had fully spread across Africa. Every civilization that has ever risen and fallen on this planet, every empire, every dynasty, every war, every scientific revolution would occur and be forgotten while you were still counting. And when you finally reached 25 trillion, you would have described the distance to our closest stellar neighbor, not the average distance to a star, the minimum, the galactic front door. Now consider the only human-made object that has ever traveled in the direction of interstellar space. Voyager 1, launched in 1977, is the farthest thing humanity has ever built and sent outward. It travels at approximately 38,000 miles per hour, which is fast by any earthly standard, roughly 22 times faster than a rifle bullet. It has been flying continuously for nearly 5 decades, never stopping, never slowing, never turning back. In all that time, it has covered roughly 15 billion miles. That sounds impressive until you measure it against the actual scale of the problem. 15 billion miles is less than one light day. Not one light year. One light day, the distance light covers in a single 24-hour period. One light day is 1/365th of a light year, and the nearest star is over 4 light years away. At its current speed, Voyager 1 would need approximately 73,000 years to reach Alpha Centauri. That is 6 times the entire span of recorded human civilization. Every pharaoh, every emperor, every president, every language ever written down, every book ever published, every song ever performed, all of it fits inside 1/6 of the time Voyager would need to reach the house next door. And when it arrived, it would not stop. It carries no braking system. It would sail past Alpha Centauri and continue into the void, a frozen relic tumbling through darkness with no destination and no one left to receive its signal. Scale outward from there, and the numbers become difficult to hold in the mind. Sirius, the brightest star in our night sky, sits 8.6 light years away, about 50 trillion miles. Vega is 25 light years out. Betelgeuse, the red giant marking Orion's shoulder, blazes from roughly 700 light years distant. These are not exotic, far-flung objects at the edge of the observable universe. These are ordinary stars in our immediate galactic neighbourhood, and the distances between them are already so vast that Voyager's 5-decade journey represents a trivial, almost laughably small fraction of what would be required to cross them. The Milky Way galaxy itself spans approximately 100,000 light years from edge to edge, roughly 588 quadrillion miles. Our solar system sits about 26,000 light years from the galactic centre. Light leaving one edge of the galaxy needs 100,000 years to reach the other side. Not a spacecraft, light. The fastest thing in the universe, travelling at 670 million miles per hour, requires 100,000 years just to cross our single galaxy. A human lifetime is roughly 80 years. Light crosses the galaxy in a time span equal to 1,250 consecutive human lifetimes placed end to end. There is a thought experiment that makes this concrete. Shrink the entire Milky Way down to the size of the continental United States. At this scale, each star becomes a grain of fine dust, barely visible to the naked eye. Our Sun and Alpha Centauri become 2 grains sitting about 4 inches apart. That seems manageable, but the next nearest Sun-like star with a potentially habitable planet might be several feet away. A civilization 1,000 light years from Earth would be in a different state entirely. The full width of the galaxy, 100,000 light years, stretches from the Atlantic coast to the Pacific. Most of that map, the overwhelming majority of it, is blank. Not filled with stars, not crowded with systems. Empty. The galaxy looks dense on a poster. In reality, it is defined almost entirely by the space between things. This is the foundation of everything that follows. Distance is not merely an inconvenience for interstellar travellers. It is not the kind of obstacle that a bigger engine or a bolder crew can push through. It is a physical reality, measured in units that dwarf every framework of perception the human brain possesses. Before the question of alien visitation can be taken seriously, this scale must be confronted honestly, not estimated, not gestured at with vague words like vast or enormous. Confronted with actual numbers, actual travel times, actual distances that have to be crossed mile by mile, because there is no shortcut. The universe does not offer shortcuts. It offers distance and then more distance, and then more beyond that. The speed of light is the universe's hardest law. Every discussion about interstellar travel eventually reaches the same wall, the speed of light. It gets mentioned casually, treated as a kind of speed limit that advanced civilization might one day find a way around, the way early engineers found ways around the supposed limits of steam power or the sound barrier. The analogy feels natural. Technology progresses. Barriers fall. What seems impossible today becomes routine tomorrow. Surely, the speed of light is just another challenge waiting for a sufficiently clever solution. It is not. The speed of light is not a barrier in the engineering sense. It is not a limitation of current materials or current energy sources or current understanding. It is a structural property of the universe itself, woven into the geometry of space-time at a level so fundamental that no amount of technological progress can negotiate with it. Understanding why requires understanding what the speed of light actually is, and why it holds the position it does in the laws of physics. Light travels at approximately 186,000 miles per second, or about 670 million miles per hour. This is extraordinarily fast by any human scale of reference. At this speed, light circles the Earth more than 7 times in a single second. It travels from the Earth to the Moon in about 1.3 seconds, from the Earth to the Sun in roughly 8 minutes. These are numbers that make light seem like an almost instantaneous courier across the solar system. But light does not set the cosmic speed limit because it happens to be fast. It sets the speed limit because of what it represents within the mathematics of space-time. In 1905, Albert Einstein published his special theory of relativity, which built a new description of how space and time behave when objects move at high velocities. The theory did not merely update the physics of motion. It revealed that space and time are not separate, independent backdrops against which events unfold. They are components of a single 4-dimensional fabric, space-time. And the speed of light is a fundamental constant of that fabric. It appears in the same equations that describe how energy and mass relate to each other, how time passes differently for moving objects, and how the geometry of the universe is structured. The speed of light is not a feature of light specifically. It is the speed at which any massless particle or wave must travel through a vacuum. It is the speed of causality itself, the maximum rate at which any influence, any signal, any piece of information can propagate from one point in space-time to another. What this means for any object with mass is deeply unfavorable. As a massive object accelerates, it requires progressively more energy to increase its speed. This is not a linear relationship. It is a curve that grows steeper with every increment of velocity and becomes infinitely steep as the object approaches light speed. At 10% of light speed, the energy required to accelerate further is already significantly greater than classical mechanics would predict. At 50%, the discrepancy becomes dramatic. At 90%, the effective mass of the object, the resistance it presents to further acceleration, is more than twice its rest mass. At 99%, that factor exceeds 7. At 99.9%, it surpasses 22. Each step closer to light speed demands exponentially more energy for each additional fraction of a percent of gain. The curve never levels off. It approaches a vertical asymptote at exactly light speed. Reaching it would require infinite energy. You cannot produce infinite energy. Nobody can. The universe does not contain infinite energy in any accessible form. Light speed is therefore not a barrier that a more powerful engine will eventually breach. It is the shape of the room. You cannot break through walls you are made of. This has been confirmed not by theoretical argument alone, but by direct experimental observation, repeated thousands of times across more than a century of increasingly precise physics. Particle accelerators around the world routinely hurl subatomic particles to 99.9999% of the speed of light. The energy required to reach each successive decimal place of that fraction increases dramatically, exactly as relativity predicts. The Large Hadron Collider at CERN accelerates protons to within a fraction of a percent of light speed, and doing so requires an installation spanning 17 miles in circumference and consuming as much electricity as a small city. All to accelerate particles with masses of approximately 1.67 times 10 to the power of minus 27 kilograms, individual protons. The energy requirement scales with mass. Any object large enough to be called a spacecraft faces energy demands that are not merely impractical, but physically incompatible with any energy budget the universe can provide. There is a version of the advanced civilization argument that surfaces here. It says, what if a future civilization discovers new physics? What if relativity turns out to be incomplete, the way Newtonian mechanics turned out to be incomplete, and whatever replaces it permits speeds we currently think are impossible? This sounds like reasonable scientific humility. It is not. Newtonian mechanics was incomplete at the extremes, at very high velocities and very strong gravitational fields, but it was not wrong within its domain. Relativity extended physics into those extreme regimes and superseded Newtonian mechanics in the cases where they conflicted. But relativity has not been shown to be wrong anywhere. It has been tested to extraordinary precision across an enormous range of conditions and has passed every test. The speed of light as a universal limit has been confirmed by GPS satellite corrections, by gravitational wave detection, by cosmic ray physics, and by a century of particle accelerator experiments. It is not a provisional hypothesis awaiting revision. It is one of the most thoroughly verified facts in the history of science. Future physics may reveal new phenomena within its own domain, just as relativity revealed new phenomena within its domain. But unseating the speed of light as a hard limit would require overturning not just one equation, but the entire mathematical architecture of modern physics simultaneously. The probability of this is not meaningfully greater than zero. What this means practically is that any spacecraft traveling between stars must do so at sublight speeds. The highest velocities realistically discussable in serious propulsion research range from about 0.1% to perhaps 10% or 20% of light speed, and even reaching the lower end of that range requires engineering that does not yet exist. At 10% of light speed, a velocity roughly 150 times faster than anything humanity has ever built. The journey to Alpha Centauri takes 42 years. A star 100 light-years away takes 1,000 years. A star 1,000 light-years away takes 10,000 years. And 1,000 light-years is not a distant or exotic location within the Milky Way. It is a modest distance, a small fraction of the galaxy's 100,000 light-year diameter. The speed of light does not just limit how fast ships can travel, it limits how fast information can travel. A radio signal or laser transmission moves at exactly light speed, which means it takes 4.24 years for a message to reach Alpha Centauri and another 4.24 years for a reply to return. A conversation with a ship in transit becomes increasingly impractical as the distance grows, eventually collapsing into an exchange of historical artifacts. Messages sent by people who may be dead before the reply arrives, referencing situations that have long since resolved or catastrophically deteriorated. Communication across interstellar distances is not slow. It is structurally broken in ways that no technology can fix, because technology cannot make information travel faster than light without violating the same physical laws that cap spacecraft velocities. The speed of light is the universe's hardest law. It applies to everyone equally. It applied before any civilization existed to discover it. It will apply long after the last civilization has gone dark. No amount of intelligence, ambition, or technological sophistication changes what it costs to move mass through space at a meaningful fraction of that speed, and nothing can exceed it. This is where the analysis of interstellar travel must begin, because every subsequent constraint flows from this one. The kinetic energy price tag of interstellar travel. Distance and the speed of light define the problem. Energy is where the problem becomes catastrophic, because the only way to cover interstellar distances in any time frame shorter than geological epochs is to go fast. And going fast costs energy, not in the way that driving a car costs fuel, or even in the way that launching a rocket costs propellant. It costs energy in quantities so staggering that the numbers require careful unpacking before they can be meaningfully compared to anything in human experience. Start with the most basic physics. The kinetic energy of a moving object is determined by two things: its mass and its velocity. For objects moving at speeds well below light speed, the relationship is straightforward. Kinetic energy equals 1/2 times the mass times the velocity squared. The squaring of velocity is the critical detail. It means that doubling the speed of an object does not double its kinetic energy. It quadruples it. Tripling the speed multiplies the kinetic energy by 9. Each incremental increase in velocity costs disproportionately more than the last. This relationship is not unique to interstellar travel. It is basic mechanics, observable in everything from car crashes to bullet impacts. At the extreme velocities required for interstellar travel, relativistic effects add further penalties on top of this already punishing baseline. Consider a specific, concrete example. Take a robotic probe with no crew, no life support, no artificial gravity, just instruments, a communication system, a power source, and a structural frame. Give it a mass of 1,000 kilograms, roughly the weight of a small car. To accelerate this probe to 10% of the speed of light, a velocity of approximately 67 million miles per hour requires roughly 4.5 times 10 to the power of 17 joules of kinetic energy. Written out, that is 450 quadrillion joules. To understand what that number means in practical terms, consider a large nuclear power plant. A typical facility produces approximately 1 gigawatt of continuous electrical power. 1 gigawatt equals 1 billion joules per second. Running that plant at full capacity for an entire year generates roughly 3.15 times 10 to the power of 16 joules of energy. The energy required to accelerate a 1,000 kilogram probe to 10% of the speed of light is therefore equivalent to about 14 years of total output from a single nuclear power plant operating continuously at full capacity. 14 years of uninterrupted operation from a facility that costs billions of dollars to construct and supplies electricity to roughly 1 million homes. All to propel a car-sized robotic spacecraft to a speed that still results in a 42-year journey to the nearest star. Now compare that to humanity's total annual energy production. Every power plant, every combustion engine, every solar installation, and every wind turbine on Earth combined generate approximately 5.8 times 10 to the power of 20 joules each year. The energy required for this single 1,000 kilogram probe represents roughly 1/1,300th of total global annual energy production. And that is for a single small spacecraft, with no deceleration, no return journey, no crew. Just a machine launched toward the nearest star at extreme velocity, reaching it in about 4 decades, then continuing onward into interstellar space with no means of stopping. Now consider what the energy requirement for deceleration means. A probe arriving at Alpha Centauri at 10% of light speed will cross the entire star system in a matter of hours without braking. To actually stop, to slow from 67 million miles per hour to something that allows useful observation, requires the same energy as acceleration, applied in reverse. The energy budget has just doubled. Not a probe that arrives and studies the system, just a probe that arrives and stops. 2 times the already extraordinary energy cost, for the minimum useful outcome of the simplest conceivable interstellar mission. The atomic bomb dropped on Hiroshima in 1945 released approximately 6.3 times 10 to the power of 13 joules of energy. The kinetic energy of a 1,000 kilogram probe travelling at 10% of the speed of light would be equivalent to roughly 7,000 Hiroshima-level detonations concentrated into the motion of a single, small spacecraft. 7,000 nuclear-scale explosions, not released outward in a blast, but fully converted into forward momentum, just to propel a car-sized robotic probe toward the nearest star. And even with that staggering amount of energy, the journey would still take 42 years to arrive. Now scale up. A probe weighing 1,000 kilograms is not a spacecraft. It cannot carry a crew, life support, food, water, radiation shielding, waste recycling systems, or any of the other infrastructure required for biological survival. A minimal crewed vessel, not a comfortable ship, not a well-equipped exploration craft, but the absolute bare-bones minimum needed to keep even a small number of people alive in deep space for decades, would mass at least several 100,000 kilograms. Realistic estimates for a modestly capable interstellar vessel range into the millions or tens of millions of kilograms. The kinetic energy scales directly with mass. A spacecraft massing 10 million kilograms requires 10,000 times more energy than our 1,000 kilogram probe. That is the energy equivalent of 70 million Hiroshima bombs, delivered in the form of velocity, for one ship, one way, no return. This is the energy price tag that physics presents to any civilization attempting interstellar travel. It does not change based on how advanced the civilization is. It does not decrease as technology improves. It is set by the mass of the ship, the velocity required, the speed of light, and the equations of special relativity. An alien civilization, a million years more advanced than humanity, must pay exactly the same bill. They may be able to afford it more easily, the way a wealthier person can more easily afford an expensive purchase. But the price does not go down. The universe does not offer a discount for sophistication. The Tsiolkovsky rocket equation has no exceptions. The energy cost of interstellar travel is devastating enough when considered in isolation. But there is a second layer to the problem, one that compounds the energy challenge into something that even the most optimistic engineering proposals struggle to address. It is called the Tsiolkovsky rocket equation, and it describes a relationship so brutally unforgiving that physicists and engineers have given it an unofficial name: the tyranny of the rocket equation. Konstantin Tsiolkovsky was a Russian mathematician who, in 1903, derived the fundamental equation governing how rockets work. The equation establishes the relationship between the velocity a rocket can achieve, the speed at which it expels its exhaust, and the ratio of the rocket's initial mass to its final mass. The mathematics are not complicated. The implications are catastrophic. The core problem is this: any spacecraft that carries its own propellant must also carry the fuel needed to accelerate that propellant. The fuel itself has mass. That mass requires more fuel to accelerate. That additional fuel also has mass, requiring yet more fuel, and so on in a loop that spirals outward exponentially. To go faster, you need more fuel. More fuel means more mass. More mass means you need still more fuel to move it. The relationship between desired velocity and required fuel to payload ratio does not grow linearly. It grows exponentially. And at the velocities required for interstellar travel, the exponential function produces numbers that are not merely impractical. They are physically impossible. For chemical rockets, the kind that have powered every crewed space mission in human history, the exhaust velocity is approximately 4.5 kilometers per second. This is a hard limit imposed by the chemistry of the propellants. Rocket fuel releases energy when it combusts, and the energy available from any chemical reaction is limited by the atomic bond energies of the molecules involved. You cannot get more exhaust velocity from a chemical rocket than the chemistry allows, regardless of how elegantly the engine is engineered. At 4.5 kilometers per second exhaust velocity, reaching even 1% of the speed of light, 3,000 kilometers per second, would require a fuel-to-payload ratio so extreme that the spacecraft would need to be almost entirely fuel. Reaching 10% of light speed with chemical propulsion is not impractical. It is mathematically impossible. The required fuel mass exceeds the mass of everything that has ever existed in the observable universe. The exponential function grows that aggressively when you push it far enough. Nuclear propulsion offers a meaningful improvement. A nuclear thermal rocket, which heats propellant using a fission reactor rather than chemical combustion, can achieve exhaust velocities roughly 2 to 3 times those of chemical rockets. Nuclear pulse propulsion, the theoretical concept developed under Project Orion in the late 1950s and early 1960s, proposed detonating a sequence of nuclear bombs behind the spacecraft to generate thrust. Orion's designers estimated it could potentially reach 3% to 5% of light speed under optimistic assumptions. This represented genuine progress over chemical rockets. It also required a spacecraft the mass of an ocean vessel, a stockpile of thousands of nuclear warheads, and a method of surviving the repeated nuclear detonations close enough to the ship to provide thrust. Even at 3% of light speed, the journey to Alpha Centauri takes over 140 years. For stars farther than a few dozen light years, the journey time measured in centuries or millennia, and the crew would never survive to arrive. Fusion propulsion is frequently cited as the most promising theoretical option currently within the boundaries of known physics. Controlled nuclear fusion, the process that powers stars, combining hydrogen nuclei into helium and releasing vast amounts of energy, produces roughly 4 times more energy per kilogram of fuel than fission, and hydrogen is the most abundant element in the universe. A functional fusion rocket could theoretically achieve exhaust velocities of several percent of light speed, making interstellar missions conceivable on timescales of centuries rather than millennia for the nearest stars. The fuel-to-payload ratios, while still demanding, would not reach the physically impossible extremes that chemical or fission propulsion encounters. There is one problem: we do not have fusion. Despite more than 70 years of sustained research, hundreds of billions of dollars of global investment, and the intellectual effort of generations of physicists and engineers, controlled sustained fusion remains beyond human capability. The challenge is containment. Fusion requires heating hydrogen isotopes to temperatures exceeding 100 million degrees Celsius, roughly 6 times hotter than the core of the Sun. At these temperatures, matter exists as plasma, a state so energetic that it destroys any physical material it contacts. Current approaches use powerful magnetic fields to suspend the plasma in a vacuum, preventing it from touching the reactor walls. This magnetic confinement must be maintained with extraordinary precision, while the plasma churns in turbulent instabilities that have defied reliable control for decades. As of today, no fusion reactor has produced more energy than it consumed in a sustained, repeatable manner. The International Thermonuclear Experimental Reactor, ITR, the most ambitious fusion project ever undertaken, has been under construction for decades at a cost exceeding $25 billion. Its goal is to demonstrate net energy gain for the first time. If it succeeds, it will produce approximately 500 megawatts of fusion power for periods of minutes. That is a breakthrough of enormous scientific significance. It is also a distance of several orders of magnitude away from the sustained gigawatt-scale power outputs that a fusion-powered starship would require, maintained not for minutes, but for years of continuous acceleration. The gap between a successful ITER experiment and an interstellar fusion drive is not a gap that one generation of engineers will close. Even antimatter, the most energy-dense fuel that physics theoretically permits, does not solve the rocket equation for practical interstellar travel at the scale required. It comes closer than any other option. But the manufacturing challenge is so extreme that it effectively removes antimatter from any realistic consideration. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass directly into energy. Nothing beats this. Chemical combustion converts less than a 10 millionth of a % of fuel mass into energy. Fission converts about 0.1%. Fusion converts about 0.7%. Antimatter annihilation converts 100%. It is the theoretical ceiling of fuel energy density. The total amount of antimatter ever produced by every particle accelerator in human history adds up to approximately 20 nanograms, 20 billionths of a gram. This quantity would be invisible to the naked eye. It would not register on a kitchen scale. Producing a single gram of antimatter using current technology would require an estimated $25 trillion in energy costs, more than the GDP of the United States. Producing the hundreds of kilograms needed to fuel even a small interstellar probe would require energy inputs equivalent to the entire output of human civilization sustained for millions of years. These are not engineering challenges. They are statements about the fundamental mismatch between what interstellar travel requires and what any civilization grounded in known physics can realistically produce. The rocket equation does not care about the civilization attempting to obey it. It applies to anyone made of matter, operating in a universe governed by the same physical constants that govern ours. Alien engineers face the same exponential curve when they sit down to design an interstellar vehicle. The specific solutions available to them may differ. The constraint does not. Antimatter is the best fuel physics will ever allow. Antimatter sits at the theoretical ceiling of what propulsion physics permits. Every other fuel source, chemical, fission, fusion, is measured against it and found less efficient by factors ranging from 1,000 to 1 billion. It is the endpoint of the energy density spectrum, the answer to the question, if you could convert mass directly into thrust with perfect efficiency, what would that look like? The answer is antimatter annihilation. And even this ultimate fuel does not make interstellar travel straightforward. It makes it possible only in the most optimistic theoretical framing, while remaining so far beyond practical production capability that discussing it as an engineering option requires some intellectual generosity. The physics of antimatter are straightforward. Every particle of ordinary matter has a corresponding antiparticle with identical mass but opposite charge and quantum properties. The electron's antiparticle is the positron. The proton's is the antiproton. When a particle and its antiparticle meet, they annihilate instantly, converting their combined mass into energy in the form of high-energy photons, gamma rays, along with secondary particles. This process follows Einstein's famous equation from Albert Einstein, E equals mc squared. The c squared term is immense. The speed of light is 3 times 10 to the power of 8 meters per second. Squared, that becomes 9 times 10 to the power of 16. If 1 kilogram of antimatter annihilates with 1 kilogram of ordinary matter, the total mass converted is 2 kilograms. That reaction releases approximately 1.8 times 10 to the power of 17 joules of energy. For comparison, 1 kilogram of the most efficient chemical rocket propellant releases on the order of 10 megajoules, about 10 million joules, or 1 times 10 to the power of 7. Antimatter, therefore, is roughly 9 billion times more energy dense than chemical fuel. That extraordinary density is why antimatter propulsion represents the theoretical upper limit of energy storage using known physics. For an antimatter-propelled spacecraft, the fuel efficiency advantage over chemical or even fusion propulsion is extraordinary. Calculations for an antimatter rocket using proton-anti-proton annihilation suggest that a spacecraft could theoretically reach Alpha Centauri in roughly 40 years at moderate acceleration, requiring a fuel-to-payload ratio that, while still demanding, is not physically impossible in the way chemical or fission rockets are. Some more optimistic designs envision journey times to the nearest stars of under 10 years, with more aggressive acceleration profiles. For the first time in the survey of interstellar propulsion options, the numbers do not immediately produce physically absurd results. And then the production problem arrives and erases the optimism entirely. Antimatter does not exist in nature in any usable form on or near Earth. The universe is overwhelmingly dominated by ordinary matter. And while antimatter is produced in tiny quantities by certain radioactive decay processes and cosmic ray interactions, it annihilates almost instantly upon contact with the surrounding matter. To produce antimatter in usable quantities, it must be manufactured in particle accelerators by colliding high-energy beams of ordinary particles and capturing the antimatter produced in the resulting annihilation events. This process is extraordinarily inefficient. The energy required to produce antimatter via particle accelerator vastly exceeds the energy that the antimatter itself contains when used as fuel. Current production yields less energy back than is invested by a factor of billions to one. As noted earlier, the total antimatter ever produced in human history amounts to approximately 20 nanograms. At current production rates and costs, manufacturing a single gram would take thousands of years and consume more energy than Earth's power grid produces in centuries. Scaling to the kilograms or metric tons needed for a functional interstellar mission is not a matter of building more accelerators. The energy inputs required would exceed everything humanity produces by many orders of magnitude, sustained for timescales that are geologically significant. There is no projected technological trajectory in any field of physics or engineering that leads to antimatter production at these scales within any time frame that makes interstellar travel relevant to a living civilization. This matters beyond the specific case of antimatter, because antimatter represents the theoretical best case. If the best case fuel is this far from practical reality, then every other propulsion option is further still. The problem is not merely that we lack the right technology. The problem is that the energy demands of interstellar travel, even under the most favorable assumptions physics permits, are incompatible with any realistic energy budget that a planet-bound, star-bound, or even galaxy-spanning civilization could assemble using matter and the laws of thermodynamics that govern it. There is a concept in engineering called the existence proof, demonstrating that something is physically achievable by showing at least one way it could be done that does not violate known physics. For interstellar travel at meaningful velocities using self-contained propulsion, no clean existence proof has been established. Every proposed method either runs into the rocket equation at the fuel-to-payload ratio stage, or into the production problem at the fuel availability stage, or into the energy budget problem at the civilization scale resource allocation stage. The options narrow from impractical with current technology to impossible in principle given the laws of physics as the analysis deepens. What physics has established is not that no propulsion concept has any merit, but that the floor, the minimum cost for the minimum useful mission, is already staggeringly high. And that floor is set by constants of nature that do not respond to engineering ingenuity. An alien civilization confronting these numbers faces the same calculation. Their technology may be superior. Their energy production may be orders of magnitude greater. But the bill that physics presents does not diminish with technological advancement. It simply becomes a question of whether the civilization's resources are large enough to pay it. And the bill is large enough that even stellar-scale energy budgets buy only modest interstellar capability, one ship at a time, to the nearest few stars. The interstellar medium becomes lethal at relativistic speed. The space between stars is described as a vacuum, and in a broad sense this is accurate. The interstellar medium has a density of roughly 1 atom per cubic centimetre, about 25 quintillion times less dense than the air in human lungs. By any practical standard, it is empty. But at the velocities required for interstellar travel, this near emptiness becomes one of the most dangerous environments imaginable. The same sparse material that poses no threat at the slow speeds of current spacecraft transforms into a lethal bombardment when a vessel moves at a significant fraction of light speed. The physics are simple and unforgiving. Kinetic energy depends on both mass and velocity, with velocity squared. A dust grain weighing 1 microgram, a particle smaller than a grain of table salt, is essentially harmless at the speeds of current spacecraft. At 10% of light speed, that same dust grain carries kinetic energy equivalent to roughly 100 kilograms of TNT. A single impact from a particle invisible to the naked eye delivers the energy of a large conventional bomb directly to the hull of the spacecraft. This is not theoretical. It follows directly from the same kinetic energy equations used to design everything from car safety systems to ballistic shields. The interstellar medium is not uniformly distributed, but even in the less dense regions, a spacecraft would traverse between stars. The particle flux at relativistic speeds creates a cumulative hazard that cannot be simply shielded away. A vessel with a cross-sectional area of a few hundred square meters traveling at 10% of light speed through average interstellar density would encounter thousands of dust grain scale impacts over a journey measured in decades. Each releases explosive energy at the point of contact. Hull materials that could absorb such impacts without structural failure do not currently exist, and the physics of hypervelocity impact make this a genuinely difficult material science problem rather than merely an engineering gap awaiting a solution. Beyond the occasional larger particle, there is the continuous background of individual atoms. Hydrogen, the most abundant element in the universe, fills the interstellar medium at a density of roughly 1 atom per cubic centimetre. At 10% of light speed, each hydrogen atom strikes the forward face of the spacecraft with an energy in the kilo-electron-volt range. Individual atoms at this energy are not catastrophically destructive, but the flux is constant and unrelenting. Every second of flight, every square centimetre of the ship's forward surface is being struck by a stream of high-energy protons. The cumulative effect, sustained over decades of travel, is equivalent to operating inside a continuous particle accelerator. Surface materials erode at the molecular level as atoms are knocked out of their lattice positions. The leading edge of the spacecraft is continuously sandblasted by particles moving at relativistic velocities, gradually degrading every material it contacts, regardless of how it was engineered. Protecting against this hazard requires shielding, material thick and dense enough to absorb high-energy particle impacts before they reach critical systems or biological crew members. But every kilogram of shielding is a kilogram that must be accelerated to interstellar velocities. Given the energy costs already described, the mass penalty for adequate shielding is not trivial. Estimates for effective interstellar shielding against the combined hazards of particle impacts and radiation range from tens of thousands to hundreds of thousands of kilograms for even a modest spacecraft. This mass must be paid for in fuel, and the rocket equation compounds the cost exponentially. Some proposals attempt to sidestep the impact problem by placing a thin shield, sometimes called a Whipple shield or a dust bumper, at the front of the spacecraft, designed to vaporize incoming particles before they reach the main hull. This approach has merit at low velocities and has been implemented on spacecraft within the solar system. At relativistic velocities, the physics change qualitatively. A particle hitting a thin shield at 10% of light speed does not simply deflect or fragment. The collision produces a spray of secondary particles, fragments of both the incoming object and the shield material, moving at high energies in a cone forward of the ship. Some fraction of this secondary spray reaches the hull behind the shield, with enough energy to cause damage. The shield trades a concentrated point impact for a diffuse spray of high-energy secondary particles. This reduces the worst-case impact scenarios, but does not eliminate the cumulative radiation damage from the continuous background flux. No proposed shielding solution has been demonstrated to provide adequate protection against the full spectrum of interstellar medium hazards at relativistic velocities. The problem is not primarily a materials science problem, though materials science is a limiting factor. It is a physics problem. At velocities high enough to make interstellar travel practical, the interstellar medium ceases to be empty space and becomes an energetic environment that attacks the spacecraft continuously from the moment of departure until arrival. Every hour of flight adds to the cumulative damage. Every repair consumes resources. Every compromised system increases the probability of cascading failures over a journey that may last decades or centuries. Cosmic radiation does not discriminate. The interstellar medium particle hazard is a problem of high-speed collisions. Cosmic radiation is a different category of threat entirely, one that does not require high spacecraft velocities to become lethal, and one that no material thickness can fully block. Cosmic rays are high-energy particles, primarily protons and atomic nuclei, accelerated to near light speed by some of the most energetic processes in the universe: supernova remnants, pulsar wind nebulae, active galactic nuclei. These particles permeate the galaxy. They travel in every direction. They pass through spacecraft hulls, through shielding material, through human tissue, without slowing significantly. They cannot be deflected by passive shielding the way slower particles can, because they carry so much energy that even meters of dense material reduce their flux only modestly. On Earth, humans are protected from cosmic ray exposure by a combination of the planet's magnetic field and the atmosphere. The magnetosphere deflects the lower energy portion of the cosmic ray spectrum, preventing it from reaching the surface. The atmosphere, equivalent to roughly 10 meters of water in shielding depth, absorbs much of the remainder. Even with these protections, roughly one cosmic ray particle passes through every square centimeter of Earth's surface per minute. Astronauts in low Earth orbit receive significantly higher doses because they are above most of the atmosphere and partially outside the magnetosphere. Data from the International Space Station shows that astronauts accumulate radiation exposure at roughly 10 times the rate of people on Earth's surface, contributing meaningfully to long-term cancer risk over extended missions. Interstellar space is worse, far worse. There is no planetary magnetic field. There is no atmospheric shielding. The full cosmic ray flux, including the high-energy component that Earth's magnetosphere blocks, bombards the spacecraft continuously from all directions. Measurements from NASA's Curiosity rover during its transit to Mars showed that even the 253-day journey through interplanetary space exposed the mission systems to radiation doses that would exceed NASA's career exposure limits for human astronauts. Mars transit takes roughly 8 months. An interstellar journey at 10% of light speed to Alpha Centauri takes 42 years. The cumulative radiation dose over a 42-year interstellar transit would be lethal many times over for any biological crew without extraordinary shielding. And extraordinary shielding, the kind that meaningfully attenuates the high-energy galactic cosmic ray component, requires material thicknesses and mass densities that are not compatible with any realistic spacecraft design. Studies of cosmic ray shielding for hypothetical Mars missions, which involve only months of exposure, suggest that effective protection against galactic cosmic rays would require surrounding the crew with meters of water, polyethylene or regolith, adding masses on the order of hundreds of metric tons for even a small crew volume. For a 42-year journey, the required shielding depth increases in proportion to the mission duration, assuming the goal is to keep cumulative exposure below lethal thresholds. The masses involved become prohibitive when combined with the already enormous energy costs of acceleration. There is also a category of cosmic radiation hazard that shielding cannot address at all: secondary particle showers. When a high-energy cosmic ray impacts shielding material, the collision produces a cascade of secondary particles, neutrons, gamma rays, pions, muons, that radiate outward from the impact point. Some fraction of these secondaries penetrate deeper into the structure than the primary particle would have, reaching crew compartments or critical electronics through pathways that bypass the shielding geometry. Increasing shielding thickness reduces the primary flux, but increases secondary shower production, creating a point of diminishing returns beyond which adding more shielding produces marginal benefit, while adding mass with a significant fuel cost. The radiation environment of interstellar space is not merely a health hazard for biological crew members, it is also a degradation mechanism for electronics and structural materials. Cosmic ray particles cause displacement damage in semiconductor devices, knocking atoms out of their crystal lattice positions and creating defects that accumulate over time, gradually changing the electrical properties of transistors, memory cells, and sensor elements. Over years and decades of exposure, this damage degrades the performance of unshielded electronics in ways that are difficult to repair without physical replacement of affected components. A spacecraft carrying decades of spare electronics must account for this mass in its design. A spacecraft that cannot carry sufficient spares faces a slow degradation of its computational and navigational systems throughout the mission, with no possibility of external replacement. The radiation problem does not yield to a straightforward engineering solution. It is bounded on one side by the physical properties of cosmic ray particles, their energies, their penetrating power, their interaction cross-sections, and on the other side by the mass constraints imposed by the propulsion energy budget. These two boundaries squeeze the design space for any interstellar vehicle into a region that existing physics cannot bridge with any known material or shielding concept. Time dilation is a trade, not a solution. Spend enough time in any conversation about interstellar travel and time dilation will be offered as the answer. It sounds compelling. Special relativity predicts that time passes more slowly for objects moving at high velocities relative to stationary observers. A crew travelling at 90% of light speed ages at roughly 44% the rate of people who remain behind. At 99% of light speed, the crew ages at about 14% the rate of the home world. Push velocities high enough, and the subjective journey time for the crew could be compressed to years or even months, even as decades or centuries pass back on Earth. The math is real. The effect has been confirmed experimentally. It sounds like a gift, the universe offering a way to compress impossible distances into manageable, subjective timeframes. It is not a gift. It is a trade, and the terms of the trade are terrible. Begin with what time dilation actually offers. A crew travelling at 99% of light speed to a star 100 light-years away experiences approximately 14 years of subjective time during the journey. From their perspective, they age 14 years, arrive, and can potentially explore their destination while still biologically capable. This is genuinely useful, in isolation. But while those 14 years pass aboard the ship, 100 years pass on the homeworld. Every person the crew knew who was not on the ship has aged a full century. Parents, siblings, friends, colleagues, all dead if they were alive at departure. The civilization they left behind has had 100 years to change. Technologies, governments, languages, cultural references, all transformed. The crew arrives not as explorers returning from a long journey, but as time travellers displaced a century forward. Whatever mission they were sent to accomplish was defined by a world that no longer exists in the form that defined it. And the return trip doubles the displacement. A round trip at 99% of light speed to a star 100 light-years away takes roughly 28 years of subjective crew time. It takes 200 years of homeworld time. The crew returns to a civilization separated from their departure by 2 centuries. Their historical records are museum artifacts. Their mission parameters are obsolete. Their institutional sponsors are dissolved or unrecognizable. They return as strangers in a future that moved on without them. This temporal disconnection is not merely a social or emotional problem. It is a mission architecture problem. Interstellar exploration requires sustained, coherent purpose across the full duration of the voyage. The mission must be worth completing when it ends, not just when it begins. If the civilization that defined the mission has transformed beyond recognition, by the time the crew arrives, the original purpose may be irrelevant. The original sponsors may be gone, and the information the crew collects may have no audience left to receive it meaningfully. Time dilation does not compress the mission for the civilization. It extends the separation between the travelers and everyone else to the point where the mission loses coherence. Now confront what it costs to achieve relativistic time dilation in the first place. Getting to 99% of light speed is not a modest engineering challenge. The energy required to accelerate a spacecraft to this velocity scales by the Lorentz factor, the relativistic correction that accounts for the increasing resistance to acceleration as an object approaches light speed. At 99% of light speed, the Lorentz factor is approximately 7. The energy required to reach this velocity is not merely 7 times the classical kinetic energy calculation. The relationship between velocity and energy in the relativistic regime means that the effective fuel requirement to achieve time-dilating velocities is many times greater than the already enormous figures discussed for 10% of light speed. Every additional decimal place of velocity costs exponentially more energy. Achieving the time dilation benefits requires paying an energy price that is orders of magnitude beyond the already staggering costs associated with more modest interstellar velocities. Time dilation is therefore not a solution to the interstellar travel problem. It is a trade. Compress the subjective journey time for the crew at the cost of exponentially greater energy expenditure and permanent, irreversible disconnection from the civilization that launched the mission. The travelers experience a shorter journey. Everyone else experiences their indefinite absence. The mission becomes self-contained and isolated from the moment of departure, cut off not just by distance, but by the forward march of time that the crew is racing through at a different rate than the world they left behind. There is one additional dimension of time dilation that the optimistic version of the argument glosses over. The time dilation calculations assume constant high-velocity travel, but acceleration and deceleration phases, the beginning and end of every journey, occur at sub-relativistic velocities where dilation is minimal. A realistic interstellar mission profile involves a long acceleration phase, a cruise phase at near constant velocity, and a deceleration phase. Only the cruise phase provides meaningful time dilation. For missions to nearby stars, the cruise phase may not be long enough relative to the acceleration and deceleration phases to provide dramatic time savings. For missions to more distant stars, the time dilation during the cruise phase is genuine, but the energy costs of reaching the required velocities for that dilation place the mission into the realm of theoretical physics rather than engineering possibility. The universe offers time dilation as a genuine feature of physics. It does not offer it for free. The price is paid in energy, in disconnection, and in the permanent transformation of the relationship between the travelers and the civilization that sent them. That price does not get cheaper as technology improves. It is set by the same physical constants that set every other price in this analysis: generation ships and the mathematics of long-term collapse. When the journey times for interstellar travel are honestly confronted, centuries to millennia even at the most optimistic velocities, a concept emerges that attempts to sidestep the individual lifespan problem. If no individual can survive the voyage, perhaps a population can. Build a vessel large enough to sustain a self-reproducing community. The original crew lives aboard the ship, has children, grows old, and dies. Their children do the same. Generation after generation is born into the ship, lives entirely within it, and dies without ever knowing anything else. Eventually, after dozens or hundreds or thousands of generations, the final generation arrives at the destination. The mission succeeds, even though no individual who launched it ever lived to see the outcome. The concept is called a generation ship, or a world ship. It has been a staple of science fiction for decades. In the abstract, the logic is airtight. If individuals cannot survive the journey, populations can relay the mission across biological time. But the moment you attempt to make the concept concrete, to actually specify what a generation ship would require to function, and to model how it would behave over meaningful timescales, every component of the idea begins to fracture. Begin with the biological minimum. A generation ship must maintain a genetically viable population across the full duration of the voyage. Genetic viability is not merely a matter of counting people. It requires sufficient genetic diversity to prevent inbreeding depression and to preserve the adaptive potential needed for a population to establish itself in a new environment at the journey's end. Population genetics research suggests that a minimum viable founding population for long-term genetic health requires at least 500 to 1,000 individuals as a bare minimum, with more robust estimates placing the number at 5,000 to 10,000 to maintain diversity across many generations without significant loss of adaptive capacity. This is not a skeleton crew of heroic volunteers. This is a small town. The ship must house, feed and sustain a small town in a sealed metal vessel for the entire duration of a journey lasting centuries to millennia. The mass implications are severe. A vessel capable of housing 10,000 people with adequate living space, agricultural capacity, water recycling, air recycling, waste processing, medical facilities, manufacturing capability, and structural integrity would mass on the order of millions to tens of millions of kilograms at minimum. This feeds back into the propulsion energy equation with brutal force. Every additional kilogram of ship mass multiplies the fuel requirement through the rocket equation, pushing the total energy budget into regimes that are extraordinary, even by stellar scale standards. The ecological challenge is, if anything, more daunting than the biological minimum population problem. A generation ship is a closed ecological system. Every molecule of water, every atom of carbon, every gram of nutrients must be recycled continuously with near-perfect efficiency, indefinitely. Nothing can be imported. Nothing can be discarded. The ship's internal ecology, its food production systems, its atmosphere processes, its water purification systems, its waste decomposition systems must function as a self-sustaining biosphere, cycling every element through the living and non-living components of the system without accumulating any deficits. No human-engineered closed ecological system has ever sustained itself for more than a few years. Biosphere 2, the most ambitious attempt at a sealed artificial ecosystem ever constructed, ran from 1991 to 1993 with 8 human inhabitants. Within 18 months, oxygen levels had dropped to dangerous lows, equivalent to the atmosphere at 14,000 feet elevation, because microbial decomposition in the soil was consuming oxygen faster than the plants were producing it. The experiment required external intervention to restore safe atmospheric conditions. 8 people. A 3-acre facility. On the surface of Earth, with gravity, sunlight and emergency backup systems available. The experiment lasted roughly 2 years before requiring outside help. A generation ship must sustain thousands of people in a sealed environment for centuries or millennia, in a vacuum, without gravity unless generated artificially, with no possibility of external intervention. The social dimension of long-duration confinement represents another category of failure that is not addressable through engineering. Human societies are not stable across centuries, let alone millennia. They fragment, reorganize, and sometimes collapse with a regularity that historical analysis makes impossible to ignore. In the past 5,000 years of documented human history, no civilization has maintained continuous institutional identity across more than a few centuries without dramatic transformation, collapse, or replacement by successor cultures. Languages drift beyond mutual intelligibility within several hundred years. Religions transform, split, and spawn entirely new theological frameworks within a few generations of doctrinal separation. Political systems that appear stable over decades reveal instabilities over centuries. Aboard a generation ship 300 years into a 2,000-year voyage, the cultural landscape would be unrecognizable to the mission's founders. The original crew, 10 to 12 generations removed from the current population, would be known only through historical records. Records that may have been selectively preserved, selectively interpreted, or partially lost through the accumulated small failures of data storage systems over centuries. The language of the original mission documents may have drifted enough that comprehensive translation is required. The cultural context in which the mission's purpose was defined has been replaced by a new culture born entirely within the confines of the ship, shaped by 300 years of closed community evolution with no external inputs, no immigration, no exchange with other cultures. The mission's purpose, defined by people dead for 2 centuries, may be reinterpreted, contested, or actively rejected by a population that had no choice in whether to participate. The ethics of generation ships are rarely confronted honestly. Every person born aboard a generation ship is conscripted into the mission before birth, assigned a life within a metal vessel without consent, and expected to maintain commitment to an objective defined by ancestors they never knew. Historical examples of populations held in involuntary confinement, prisoners, enslaved populations, isolated colonial outposts, do not suggest that multi-generational commitment to an external mission is a reliable outcome of such conditions. Rebellion, fracture, and the complete reorientation of social purpose around immediate survival concerns rather than long-term mission objectives are far more historically consistent outcomes. Mechanical degradation across civilizational timescales adds the final layer to the generation ship collapse scenario. Every system aboard the vessel, propulsion, navigation, life support, power generation, hull integrity, radiation shielding, must function without failure for the entire voyage duration. The mean time between failures for any complex system is finite. No material is immune to degradation. Metals fatigue under thermal cycling. Seals erode under constant pressure differentials. Electronics accumulate radiation damage. Lubricants break down and must be replaced. Structural components develop microfractures that propagate slowly under the stresses of acceleration, deceleration, and temperature changes. The mathematics of reliability engineering are unambiguous on this point. A system with a 99.99% annual reliability, meaning a 1 in 10,000 chance of catastrophic failure in any given year, has only about a 90% chance of surviving 1,000 years without failure. Over 10,000 years, the survival probability drops to essentially zero. For a generation ship with thousands of interdependent systems, each with its own reliability curve, the probability that all critical systems remain functional across a journey of this length approaches zero exponentially. The only way to extend mission survival probability to acceptable levels is through extraordinary redundancy, continuous maintenance, and manufacturing capacity sufficient to replace any failed component on demand. Each of these requirements adds mass. Each adds complexity. Each adds its own failure modes to the system. The generation ship concept is not an engineering challenge awaiting better technology. It is a compendium of simultaneous, interlocking, irreducible challenges, biological, ecological, social, and mechanical, each of which, individually, has never been solved for the timescales involved, and which collectively present a problem whose difficulty scales faster than any single technological advance could address. The communication blackout is total and it never ends. Every spacecraft that has ever left Earth has maintained a communication link with home. From the Apollo missions to the Voyager probes to the Mars rovers, the thread of radio contact has remained unbroken. Mission controllers on the ground receive telemetry, transmit commands, diagnose problems, and guide operations in near real time. Or, in the case of Mars missions, with a delay of up to 24 minutes in each direction, which is manageable for most operational purposes. This pattern of continuous communication with ground support is so deeply embedded in space mission architecture that it is rarely examined as an assumption. It is simply how missions work. For interstellar missions, this assumption breaks catastrophically and permanently, not because of any technical failure, but because of the hard physical limit imposed by the speed of light. Communication signals travel at exactly light speed. They cannot travel faster, and at interstellar distances, this means communication delays measured not in minutes, but in years, decades, and centuries. Consider the practical implications at each distance scale. A spacecraft travelling toward Alpha Centauri at 10% of light speed is, after 1 year of flight, approximately 0.63 light-years from Earth. A radio signal sent from Earth takes 0.63 years to reach the ship. A reply takes another 0.63 years to return. A single exchange of information requires roughly 15 months. This is already operationally difficult. Now extend the timeline. 5 years into the mission, the communication round trip takes roughly 10 years. The ship is still decades away from its destination. Instructions relevant to the ship's current situation cannot be received for years after they are sent. Replies from the crew describe conditions that are years in the past by the time they arrive at Earth. The conversation has become an exchange of historical documents rather than operational communication. By the time a ship is 10 light-years from Earth, a single round-trip communication takes over 20 years. The people who sent the last message may have changed roles, retired or died before the reply arrives. The institutional context in which the message was sent has transformed. The operational problem the message addressed has long since resolved through whatever means the crew could manage independently, or has catastrophically deteriorated in ways that the reply can no longer address. Communication at this scale is not slow. It is functionally broken. It provides historical information about past conditions, not operational support for present problems. At 100 light-years, a round-trip communication takes 200 years. At 1,000 light-years, 2,000 years. At distances that place a civilization outside our immediate galactic neighbourhood, communication delays extend to timescales that exceed the lifespan of most political institutions, most languages, and most cultures. A message sent from a civilization 1,000 light-years away arrives here 1,000 years after it was composed. Whatever circumstances prompted the message, whatever question was asked, whatever discovery was announced, whatever emergency was reported, is 1,000 years in the past by the time we read it. A reply sent immediately does not arrive for another 1,000 years, at which point 2 millennia have elapsed since the original communication. For a ship in interstellar transit, the communication blackout is not merely a practical inconvenience. It is a fundamental architectural reality that shapes every aspect of how the mission must be designed and operated. Within years of departure, the crew is operationally independent. Mission controllers on the homeworld cannot respond to problems in real time. Decisions must be made locally by the crew with whatever information and resources are available aboard the ship, with no possibility of consultation or external expertise. Within decades, even strategic guidance from home is unreliable. By the time updated mission parameters arrive, they reflect an understanding of the ship's situation that is years out of date. Within centuries, the communication channel has ceased to function as anything resembling a connection between the mission and the civilization that launched it. Messages continue to travel in both directions, but they describe worlds that no longer exist by the time they arrive. This total operational isolation has profound implications for mission design. Every contingency must be anticipated before departure. Every expertise must be represented among the crew. Every spare part, every tool, every material needed for any conceivable repair must be aboard the ship, because nothing can be resupplied and no external expert can be consulted in any useful time frame. The mission must be self-sufficient, not for days or weeks, but for the entire duration of the voyage, which for stars beyond the nearest few means centuries or millennia of complete operational independence from any external support. No human mission has ever been designed to these standards. The International Space Station requires continuous resupply. Mars missions under development assume Earth contact delays of under 25 minutes. Even the Voyager probes, the most operationally independent spacecraft ever launched, have required active engagement from teams of engineers at the Jet Propulsion Laboratory to address anomalies. Engineers who can communicate with the spacecraft with a delay of roughly 22 hours in each direction. Scaling from a 22-hour communication delay to a 40-year communication delay is not an incremental engineering challenge. It is a categorical transformation in what mission architecture must look like and what capabilities must be permanently embedded in the ship and crew before departure. The communication blackout also affects the home civilization's ability to know what happened. A mission to a star 100 light-years away, travelling at 10% of light speed, takes 1,000 years to arrive. The crew's first transmission from the destination takes another 100 years to reach Earth. The first news of whether the mission succeeded or failed arrives 1,100 years after departure. The civilization that receives this news is separated from the civilization that launched the mission by more than a millennium. Whether anyone is still interested in the outcome, whether the mission's purpose remains relevant, whether the receiving civilization even maintains continuity with the launching civilization, none of this is guaranteed over 1,100 years. The mission completes in a future that the people who built the ship never lived to see, and reports its results to an audience that may have no meaningful connection to the culture that defined its objectives. The communication blackout is not a solvable problem. It is a physical constraint imposed by the same light speed limit that bounds spacecraft velocities. The only way to reduce communication delays is to reduce distances, and reducing interstellar distances brings us back to the energy and propulsion problems that have no solution within known physics. The blackout is permanent, it is total, and it begins accumulating from the moment a ship passes beyond the range where communication delays become operationally significant, which for interstellar missions is measured in years rather than the hours or days that characterize solar system exploration. Any alien civilization contemplating a mission to Earth faces this same constraint. Their communication with the home world degrades from real-time to historical correspondence to total silence as the mission progresses. By the time a ship launched from a star 1,000 light-years away is halfway to Earth, 5,000 years of travel time have elapsed. A message home takes 500 years to arrive. A reply takes another 500. The ship is on its own, has been on its own for virtually its entire voyage, operating without guidance, without support, without any meaningful connection to the civilization that built it. Whatever purpose the mission was launched with must survive intact through 5,000 years of isolation, mechanical degradation, generational cultural drift, and the relentless entropy of a closed system operating in the most hostile environment in the known universe. The communication blackout does not merely complicate interstellar missions. It transforms them into something fundamentally different from every space mission human civilization has ever attempted or planned. It creates an unbridgeable operational gap between the mission and its origin, and it does so not gradually but structurally from the physics of how information propagates through the universe. Navigating across light years is a precision problem that compounds into catastrophe. Every spacecraft ever launched by humanity has navigated using a framework that takes certain things for granted. There are tracking stations on Earth. There are radio signals bouncing between the vessel and the ground. There are known reference points, the positions of planets, the geometry of the solar system, that allow mission controllers to calculate exactly where the spacecraft is, where it is going, and what corrections are needed to keep it on course. The Deep Space Network, NASA's global array of large radio antennas, can track a spacecraft billions of miles away with remarkable precision, pinpointing its location to within a few kilometers and its velocity to within fractions of a millimeter per second. This capability represents decades of accumulated expertise and engineering refinement. It is impressive, and it is completely inapplicable to interstellar navigation. The challenge of navigating a spacecraft across light years is not merely a scaled-up version of navigating across the solar system, it is a categorically different problem, because the tools and reference frameworks that make solar system navigation work either degrade severely or fail entirely at interstellar distances. Understanding why requires examining what navigation actually means, not just pointing a ship in the right direction at departure, but maintaining precise knowledge of position and velocity throughout a journey lasting decades or centuries, and making course corrections accurate enough to arrive at a destination that is itself moving through space. Start with the pointing problem. When a ship departs for Alpha Centauri, 4.24 light-years away, it must be aimed with extraordinary precision. Alpha Centauri is not stationary. It moves through space relative to our Sun at a velocity of roughly 25 kilometers per second. Over a 42-year journey at 10% of light speed, the star system moves a significant distance from where it appears to be at departure. The ship must be aimed not at where Alpha Centauri is, but at where it will be when the ship arrives. A calculation that requires precise knowledge of the star's current velocity, direction, and any perturbations to that motion from gravitational influences over the journey duration. An angular error of just 1 arc-second at departure, 1/3600th of a degree, smaller than the apparent diameter of a coin viewed from 2 miles away, translates into a positional error of roughly 20 billion miles at the distance of Alpha Centauri. That is approximately 200 times the diameter of Earth's orbit around the Sun. An error that small in terms of angle produces a missed distance that is enormous in absolute terms. Correcting this error mid-journey requires knowing that the error exists, which requires knowing the ship's precise position, which at interstellar distances is extraordinarily difficult to determine. Solar system navigation works because the ship is close enough to Earth for two-way ranging, timing radio signals to measure distance, and because the positions of solar system bodies are known well enough to use them as reference markers. At interstellar distances, two-way ranging becomes impractical because the round-trip signal time extends to years. The positions of distant stars shift slightly due to parallax as the ship moves, but extracting precise position information from these shifts requires measurements of extraordinary accuracy sustained over years, processed by systems that must themselves remain perfectly calibrated throughout the journey. Stars used as navigation reference points are not fixed. They move. Their proper motions, the slow drift of each star across the sky as it follows its own orbit around the galaxy, must be known precisely and accounted for in navigation calculations. For nearby stars, proper motions can be measured from Earth with good accuracy, but the precision required for interstellar navigation exceeds what current astrometry can provide for all but the closest and best studied stars. Even small errors in the assumed proper motion of reference stars propagate into navigation errors that grow with distance and time. Mid-course corrections are the standard response to navigation uncertainty in solar system missions. If a spacecraft drifts off course, thrust can be applied to restore the correct trajectory. But mid-course corrections in interstellar missions are extraordinarily expensive in terms of fuel. At interstellar velocities, even a small lateral correction, a sideways nudge to adjust the ship's trajectory by a fraction of a degree, requires applying force against a vessel moving at tens of millions of miles per hour. The fuel cost of such corrections, applied against a ship that has already consumed most of its propellant in the initial acceleration, may not be available. A ship designed for a one-way mission to a specific destination may lack the fuel reserves needed for significant trajectory corrections, meaning that errors at departure cannot be recovered, and the ship sails past its destination and into the void beyond. The destination itself presents an additional navigation challenge that is easy to overlook. Stars do not exist in isolation. Arriving at Alpha Centauri is not the same as arriving at a single point in space. The Alpha Centauri system contains at least 3 gravitational bodies: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri, whose mutual gravitational interactions produce complex orbital dynamics. A spacecraft entering the system must navigate these gravitational influences while decelerating from interstellar cruise velocity to something compatible with orbital insertion or planetary approach. The gravitational environment encountered during arrival will differ from what can be predicted from Earth-based observations, because the positions of the bodies within the system at the moment of arrival cannot be precisely known decades in advance. Even small deviations from predicted positions can significantly alter the gravitational forces acting on the decelerating spacecraft. If the destination star hosts planets, and the mission's purpose presumably involves investigating those planets, finding them upon arrival is another non-trivial challenge. Planets are small, dark, and move on orbital paths that will have evolved over the decades of transit time. A planet identified from Earth observations as a candidate for investigation may be on the far side of its star at the moment the ship arrives, or may have undergone changes in its observational characteristics that make it harder to identify. The ship must conduct its own astronomical survey of the system upon arrival, using instruments that have been operating in the radiation environment of interstellar space for decades to locate and characterize targets that were identified by a civilization that may have updated its understanding of the system multiple times during the journey, with no way to transmit those updates usefully. The navigation problem for interstellar travel is not solved by better computers or more sophisticated algorithms, although both would help at the margins. It is fundamentally constrained by the precision to which stellar positions and proper motions can be measured, by the information delay that prevents real-time course corrections from Earth, by the fuel budget limitations that restrict mid-course correction capability, and by the inherent complexity of arriving at a gravitationally active star system after a decades-long ballistic trajectory. Each of these constraints has a floor set by physics rather than engineering. Together, they create a navigation problem whose difficulty is not acknowledged in casual discussions of interstellar travel, but which represents a genuine and serious additional layer of the overall challenge. No known material can survive the full journey. The question of what a spacecraft is made of sounds almost mundane compared to the grand challenges of energy and distance. Materials engineering is a well-developed field. Humanity has produced remarkable structural materials over the past century: high-strength steel alloys, carbon fibre composites, titanium structures, ceramic heat shields, aerogels with extraordinary insulating properties. The steady advance of materials science has enabled progressively more capable and more durable spacecraft within the solar system. It seems reasonable to assume that future materials will be adequate for interstellar missions, even if current materials are not quite there yet. This assumption does not survive contact with the actual conditions of interstellar flight. The material environment of a spacecraft travelling at relativistic speeds for decades or centuries is qualitatively unlike anything that materials testing on Earth can replicate, and the degradation mechanisms operating in that environment attack materials through pathways that no known substance can fully resist across the required timescales. The first and most relentless degradation mechanism is radiation damage. As discussed in the chapter on cosmic radiation, the interstellar medium is permeated by high-energy particles, galactic cosmic rays, solar energetic particles during the early portion of the journey, and the flux of interstellar hydrogen atoms that become energetic when encountered at relativistic velocities. These particles interact with the atomic structure of every material they pass through. In metals and structural alloys, radiation displaces atoms from their positions in the crystal lattice, creating point defects that accumulate over time. As defect density increases, the material's mechanical properties change. It becomes harder but more brittle. Yield strength may increase initially, then degrade. Fracture toughness decreases. Materials that were ductile and damage tolerant at the start of the mission become prone to sudden, catastrophic failure under stresses they would have handled safely at departure. This process, called radiation embrittlement, is well documented in the context of nuclear reactor pressure vessels, which experience similar, though less intense, radiation environments over their operational lifetimes. Nuclear reactors are typically decommissioned after 40 to 60 years, partly because radiation embrittlement of the pressure vessel creates unacceptable fracture risk. An interstellar mission lasting centuries would expose structural materials to radiation doses many times those that force the retirement of nuclear reactor components on Earth. Polymer materials, plastics, rubbers, adhesives, composite matrix materials are far more sensitive to radiation damage than metals. Carbon-carbon bonds break under gamma-ray and particle bombardment, causing polymers to cross-link in ways that make them rigid and brittle, or to chain scission in ways that reduce molecular weight and mechanical strength. Seal materials made of elastomeric polymers, the gaskets and O-rings that maintain pressure boundaries throughout the ship, degrade through radiation exposure at rates that make their survival over centuries deeply uncertain. The loss of a single critical seal does not merely cause a leak. In a pressurized life support environment, it can trigger a cascade of failures that is irreversible without replacement parts that may no longer be available. Electronics are, in many ways, the most radiation-sensitive components aboard any spacecraft. Semiconductors, the transistors, memory cells, and logic gates that form the basis of all computing and control systems experience displacement damage from particle radiation that accumulates over the mission duration. Individual transistors are affected asymmetrically, creating increasing variability in circuit performance. Memory cells can experience bit flips, spontaneous changes in stored data values, at rates that increase with cumulative radiation dose. Control systems that were operating within specification at departure may be producing subtly incorrect outputs years into the mission, with failures too gradual to trigger obvious alarm conditions, but sufficient to degrade navigational accuracy, life support regulation, or power management over time. Radiation-hardened electronics exist and are used in military and space applications. They employ design techniques that reduce sensitivity to radiation-induced effects. But radiation hardening provides protection against radiation doses accumulated over years to decades of operation, not centuries to millennia. The total ionizing dose experienced by electronics over a 500-year interstellar journey would exceed the design limits of any radiation-hardened component ever built by many orders of magnitude. Beyond some accumulated dose threshold, no known electronic design strategy remains effective. The hull of the spacecraft faces its own unique degradation pathway at high velocities. The interstellar medium contains not just hydrogen atoms and dust particles, but also a small flux of larger objects, micrometeoroids, cometary debris and fragments of disrupted minor bodies, whose size distribution spans many orders of magnitude. At 10% of light speed, a micrometeoroid with a mass of just 1 gram carries kinetic energy comparable to a military artillery shell. The hull cannot be made thick enough to stop all possible impacts without becoming so massive that the propulsion energy budget becomes impossible. The compromise, a hull thick enough to handle the statistical majority of impacts while accepting the possibility of occasional larger strikes, means that the ship is operating with a finite and continuously decreasing margin against catastrophic penetration throughout the voyage. No material currently known, and no material theoretically predicted within the bounds of conventional condensed matter physics, is simultaneously light enough to be included in an interstellar spacecraft's mass budget, strong enough to provide structural integrity under the stresses of acceleration, deceleration, and thermal cycling, and resistant enough to radiation damage, particle impact, and fatigue to maintain these properties for centuries of continuous operation in the interstellar environment. The requirements conflict with each other. Making a material more resistant to radiation damage often requires increasing its density, which increases mass. Making a material lighter often requires accepting reduced radiation resistance or structural strength. The design space where all constraints are simultaneously satisfied does not appear to contain any known or near-term material solution. This is not a problem that waits patiently for the next generation of materials science to solve it. It is a problem whose constraints are set by fundamental physics, by the cross-sections for particle-matter interactions, by the thermodynamics of defect formation in solids, by the relationship between material density and penetration depth for high-energy particles. Future materials science may identify better solutions within the available design space. But the physics of the environment does not change. An interstellar mission requires materials that do not exist and that have no clear pathway to existence within the bounds of known physics. The second law of thermodynamics always wins. There is a law in physics that does not make headlines, does not inspire science fiction plots, and rarely appears in popular discussions of what the future might hold. It operates silently in the background of every physical process, every engineered system, every biological organism, every galaxy cluster in the universe. It has never been violated, not once, not under any conditions ever observed, and it presents an absolute, non-negotiable constraint on any system, including an interstellar spacecraft that must operate over the timescales involved in crossing the space between stars. The second law of thermodynamics states that the total entropy of a closed system always increases over time. Entropy, in physical terms, is a measure of disorder, of the number of microscopic arrangements that correspond to a given macroscopic state. A highly ordered system, with components arranged precisely in specific configurations, performing specific functions, has low entropy. The same components distributed randomly, broken, scattered, or chemically recombined into other substances represent a higher entropy state. The second law says that isolated systems evolve spontaneously toward higher entropy states. Order decays into disorder. Complex structures break down into simpler ones. Energy spreads from concentrated to diffuse. This is not a tendency or a statistical preference. It is a law as fundamental as any in physics. For an interstellar spacecraft, the second law operates simultaneously across every scale of the system. At the molecular level, the radiation environment promotes the formation of defects, the breaking of chemical bonds, and the degradation of material properties. All increases in microscopic disorder. At the component level, mechanical wear, thermal fatigue, and chemical corrosion convert well-ordered functional components into less ordered, less functional states. At the system level, every failure of a component cascades into dependent systems, increasing overall disorder faster than any single failure would suggest. At the mission level, the accumulation of small failures, small degradations, and small losses of information and capability represents an inexorable march toward a state in which the mission can no longer be carried out. The only way to fight entropy in a system is to import order from outside, to consume energy and use it to restore degraded components, replace failed parts, and maintain the complex organization that the system requires to function. This is why living organisms eat. Food is a source of chemical energy that organisms use to maintain the organized complexity of their bodies against the constant tendency of entropy to degrade biological structures. Remove the food supply and the organism dies, not immediately, but inevitably, as entropy overwhelms the organism's ability to maintain its internal order. For an interstellar spacecraft, the equivalent of food is the ship's onboard energy supply and the material resources needed for maintenance and repair. These are finite. At departure, the ship carries a fixed complement of spare parts, raw materials, manufacturing capability, and energy reserves. Some of these resources are consumed during the journey as systems are repaired and components are replaced. Unlike a living organism, the ship cannot forage for additional resources in transit. The interstellar void offers nothing useful for maintenance purposes. Every repair depletes the onboard resource pool. Over decades and centuries, the pool shrinks while the entropy of the system increases. Eventually, the resource pool is exhausted before the entropy is contained, and the ship begins to degrade faster than it can be repaired. This is not a hypothetical scenario. It is the predicted outcome of any closed system operating over sufficiently long timescales with finite resources. The mathematics of reliability engineering make it quantitative. A complex system consisting of many interdependent subsystems, each with its own mean time between failures, has an overall reliability that decreases faster than any individual subsystem's reliability would suggest, because failures in one subsystem can trigger failures in others. A spacecraft with 10,000 critical components, a conservative estimate for any vessel capable of sustaining human life over decades, has a mean time between failures that is determined not by the most reliable component, but by the least reliable, weighted by the criticality of the function it performs. For a journey lasting centuries, the required component reliability is so high that it has never been achieved by any human engineering project at any scale. Aircraft, which are among the most reliability-critical engineered systems humans operate, have structural components with design lives measured in tens of thousands of flight hours, roughly 10 to 20 years of continuous operation. Spacecraft within the solar system, operating in less mechanically stressful environments, achieve longer operational lifetimes, but still require extensive maintenance and periodic replacement of components that degrade. The Hubble Space Telescope has operated for over 30 years, partly because it was specifically designed to be serviced by astronaut maintenance crews who have made 5 separate repair missions, replacing failed components and upgrading systems. An interstellar spacecraft has no maintenance crew coming. It has no possibility of external repair. It operates in an environment far more damaging than anything Hubble has experienced, for durations far longer than any human spacecraft has ever attempted. The second law does not care about the sophistication of the civilization that built the ship. It applies to carbon fiber and to exotic alloys yet undiscovered. It applies to silicon transistors and to computational substrates not yet imagined. It applies with equal force to any physical system made of matter and operating in a universe where energy disperses and order decays. Advanced civilizations can build more robust systems, design more redundant architectures, and maintain larger reserves of repair materials. But they cannot repeal the second law. They cannot build a ship that does not degrade. They can only build a ship that degrades more slowly, and even the slowest degradation rate, extended across the centuries and millennia of an interstellar journey, reaches the same destination. Civilizational lifespans versus the length of the journey. Every argument about the feasibility of interstellar travel by advanced alien civilizations carries a hidden assumption. It assumes that the civilization doing the traveling has existed long enough to develop the required technology, and that it continues to exist throughout the duration of the mission, which, as the preceding chapters have established, spans centuries to millennia, even under optimistic assumptions. This assumption deserves direct examination, because the historical record of civilizations on the only planet we can study in detail, Earth, is not encouraging. Human civilization, broadly defined as the organized, culturally continuous, technologically developing project that has unfolded since the first agricultural settlements in the Fertile Crescent, is approximately 10,000 years old. Within that span, individual civilizations, coherent political, cultural, and institutional entities capable of coordinating large-scale projects have rarely lasted more than a few centuries before undergoing fundamental transformation, collapse, or absorption into successor cultures. The Roman Empire, one of the longest-lived and most institutionally coherent civilizations in recorded history, lasted roughly 500 years in the West before fragmenting. The Egyptian civilization endured in various forms for millennia, but its institutional and cultural identity transformed so completely across that period that the new kingdom had little meaningful continuity with the old kingdom beyond geographic location and language family. The longest surviving continuous political institution in human history, various candidates are proposed, all controversial, can be measured in centuries, not millennia. Why does this matter for interstellar travel? Because a civilization must not merely develop the technology to launch an interstellar mission. It must sustain the institutional will, the resource commitment, and the organizational coherence to actually execute a mission that takes thousands of years to complete. An interstellar mission to a star 1,000 light-years away, traveling at 10% of light speed, requires the originating civilization to remain engaged with the mission's purpose across 10,000 years of journey time. 10,000 years. The entire span of recorded human history. If the civilization that launched the mission collapses, transforms, or simply loses interest across that period, as every human civilization has done with every comparable long-term commitment, the mission becomes an orphan. A ship traveling through void with no home to report to, no institutional framework to support it, no audience to receive its findings. Consider the practical implications. A civilization launches an interstellar ship and commits to monitoring its progress for the duration of the voyage. Within a few centuries, the technology used to communicate with the ship has been superseded multiple times. The engineers who designed the communication protocols are dead. The institutional memory of how to interpret the ship's telemetry has been partially lost through turnover, organizational change, and the natural degradation of specialized knowledge that is not actively used. The original mission parameters, defined by a political and scientific context that no longer exists, are reviewed and reinterpreted by scholars who study them the way modern historians study ancient documents, as artifacts of a vanished context rather than operational guidelines. Within a millennium, the mission has become a historical curiosity. The civilization has changed enough that the original purpose of the mission, whatever it was, seems remote, perhaps incomprehensible. Other priorities have emerged. the resources devoted to monitoring a signal from a ship that will not arrive for another 9,000 years seem difficult to justify against immediate needs. The monitoring infrastructure is repurposed or decommissioned. The mission continues in the darkness, its signals arriving to receivers that are no longer listening, carrying data that no one is processing. This is not a failure of the civilization's intelligence or ambition. It is an observation about how complex social systems behave over time. They change. They respond to immediate pressures rather than long-term commitments. They lose continuity with past decisions as the people who made those decisions die and are replaced by people with different priorities. No institution in human history has maintained unwavering commitment to a single objective across 10,000 years. There is no reason to believe that alien civilizations are fundamentally different in this regard. Intelligence does not exempt a civilization from the pressures of political change, resource competition, cultural evolution, and the simple passage of time. There is also the question of civilizational survival. A civilization capable of launching an interstellar mission has achieved a remarkable degree of technological sophistication. But technological sophistication does not guarantee longevity. Human civilization is, at this moment, capable of launching probes toward nearby stars within a few generations of focused effort. It is also capable of destroying itself through nuclear war, through catastrophic climate change, through engineered biological agents, through a dozen other mechanisms that its own technology has created. The same technological sophistication that makes interstellar missions conceivable also multiplies the ways in which a civilization can fail. Fermi estimated that technological civilizations might have typical lifespans of only a few thousand years before encountering one or more of these self-destructive thresholds. If a civilization's window of interstellar capability, the period during which it has both the technology to launch missions and the social cohesion to organize and sustain them, lasts, say, a few thousand years, then it can only launch missions to stars close enough for the journey to be completed within that window. At 10% of light speed, a few thousand years of civilizational duration corresponds to missions reaching stars, perhaps 200 to 300 light-years distant. Stars at 1,000 light-years are out of reach not because the ship cannot get there, but because the civilization that launched it will not survive to care about the arrival. The galaxy's most interesting stars, the ones farthest from the originating civilization, are systematically the least reachable, not just because of distance, but because of the mismatch between journey time and civilizational lifespan. This creates what might be called the civilizational reach problem. Every civilization in the galaxy has a sphere of practical interstellar influence, determined not by its technological capability alone, but by the product of that capability and its expected lifespan. For civilizations with short lifespans, a common outcome in a universe where the same physics that enables starflight also enables self-destruction, this sphere may be remarkably small, perhaps encompassing only the dozen or so nearest star systems before time and entropy bring the civilization down. The galaxy, which appears teeming with potential destinations, is in practice accessible only within a tiny radius around each origin point. A radius determined not by engineering, but by sociological and historical constraints that no amount of technology can override. Wormholes exist in physics equations, not in space. Every serious discussion of why interstellar travel is effectively impossible eventually reaches the same response from the other side of the argument. Fine, the counter-argument goes. Conventional propulsion faces all these problems, but what about shortcuts? What about wormholes, tunnels through space-time that connect distant points directly, bypassing the need to cross the intervening distance at sublight speed? What about folding space, bending the geometry of the universe to bring origin and destination close together? These concepts appear constantly in discussions of advanced alien travel, and they draw on real physics, or at least on real mathematics. Understanding exactly why they remain out of reach requires engaging with that physics directly. Wormholes, technically called Einstein-Rosen bridges, emerged from the mathematics of general relativity in the 1930s. Einstein and Nathan Rosen showed that the equations of general relativity permit solutions describing a topological tunnel connecting two separate regions of space-time. On paper, such a structure could link 2 points in space that are arbitrarily distant from each other by conventional routes. A few 100,000 miles of tunnel could in principle connect points separated by millions of light years of normal space-time traversal. The mathematics are genuine. General relativity does produce these solutions. This is not science fiction invented by screenwriters. It is a real feature of the equations. But there is a gap, an enormous, possibly unbridgeable gap, between a solution existing in the equations and that solution describing something that exists in physical reality or can be engineered into existence. General relativity also produces mathematical solutions describing matter with negative mass, universes with different numbers of spatial dimensions, and configurations of spacetime with no physical correspondence. The equations are more permissive than the universe. The question is not whether wormholes appear in the math. It is whether they exist in nature and whether they can be created, stabilized, and traversed. Natural wormholes, if they exist at all, would form under conditions of extreme spacetime curvature, near singularities, in the immediate aftermath of the Big Bang, or in other environments where the energy density is so extreme that the topology of spacetime itself is affected. These conditions do not occur in the quiet, relatively flat spacetime of the galaxy's stellar neighborhoods. If natural wormholes ever existed, they formed in the first fractions of a second after the Big Bang and are either too small to be traversable, too unstable to persist, or have collapsed into singularities. For wormholes to be useful for interstellar travel, they must be traversable, large enough for a spacecraft to pass through, stable enough to remain open for the duration of transit, and positioned where travelers need them. The requirements for a traversable wormhole were analysed in detail by physicists Kip Thorne and Michael Morris in 1988. Their conclusion was that maintaining a traversable wormhole against the natural tendency of space-time curvature to collapse, it requires a material with negative energy density threading the throat of the wormhole. This exotic material would need to have properties that are opposite to those of all known matter. It would gravitationally repel rather than attract, would have negative mass energy, and would violate the energy conditions that all known forms of matter and energy satisfy. No material with negative energy density has ever been observed. The Casimir effect, a quantum phenomenon involving the force between closely spaced conducting plates, produces a region of slightly negative energy density between the plates, but in quantities so vanishingly small that threading a wormhole with Casimir effect exotic matter would require a setup whose energy requirements exceed all of physics in a way that is difficult to even quantify meaningfully. Some quantum field theories permit states with locally negative energy density under specific conditions, but these conditions are bounded by quantum inequalities that prevent the accumulation of negative energy in amounts sufficient for macroscopic applications like wormhole stabilization. The amount of exotic matter required to hold open a wormhole large enough for a spacecraft depends on the size of the wormhole. For a wormhole with a throat radius of a few meters, barely large enough for a small vessel, calculations suggest that the required negative energy would be comparable in magnitude to the positive energy equivalent of a large planet's mass. This would need to be concentrated at the wormhole throat with specific spatial distribution. Producing even a gram of exotic matter with the required properties is currently not possible and has no identified physical mechanism by which it might become possible. Producing the planetary mass equivalent is not an engineering challenge. It is a statement about something that physics, as currently understood, does not permit in usable form. Beyond the exotic matter problem, traversable wormholes face the causality problem. General relativity implies that a traversable wormhole could be used as a time machine. By moving one end of the wormhole at relativistic speeds and then traversing it, a traveller could in principle arrive at the other end before they departed in the external reference frame. This creates causal paradoxes, situations where effects precede their causes, that most physicists regard as strong evidence that the universe does not permit traversable wormholes. Stephen Hawking proposed what he called the chronology protection conjecture, the idea that the laws of physics conspire to prevent the creation of time machines, and therefore prevent the creation of traversable wormholes. While the conjecture remains unproven as a theorem, it is supported by the observation that quantum effects near a would-be time machine or wormhole tend to produce enormous energy densities that would destroy the structure before it could be used. The bottom line on wormholes is this: they are permitted by the mathematics of general relativity under conditions requiring exotic matter that has never been observed, cannot currently be produced even in principle, and may not be physically realizable in any form. The engineering requirements for a traversable wormhole are not merely beyond current capability. They are beyond any capability that can be sketched out even theoretically using known physics. An alien civilization, no matter how advanced, cannot build what the universe does not provide the materials to build. The Alcubierre drive requires physics that does not exist. The Alcubierre drive is the most mathematically sophisticated proposal for faster-than-light travel ever put forward in a serious scientific context. Published by Mexican physicist Miguel Alcubierre in 1994 in the journal Classical and Quantum Gravity, it describes a space-time geometry in which a spacecraft could travel between 2 points faster than light would take to cover the same distance, not by accelerating through space, but by contracting space in front of the vessel and expanding it behind, surfing a wave of space-time distortion from origin to destination. Because the ship is not moving through space, but is instead carried by the movement of space itself, it sidesteps the relativistic prohibition on massive objects reaching light speed. The mathematics are internally consistent within general relativity. The paper was published in a peer-reviewed journal. It has been cited thousands of times. In some circles, it is treated as a genuine blueprint for a technology that advanced civilizations might have already mastered. The gap between what the Alcubierre metric describes mathematically and what it requires physically is so vast that the word blueprint is almost comically inappropriate. Examining the physical requirements of the Alcubierre drive reveals not a technology awaiting development, but a mathematical curiosity built on foundations that the universe may simply not provide. The first and most fundamental requirement of a warp drive is exotic matter, specifically matter with negative energy density arranged in an exact geometric configuration around the spacecraft, to create and sustain a warp bubble. This is the same exotic matter constraint that makes traversable wormholes physically implausible. Different mathematics, same impossible material property. In 1994, physicist Miguel Alcubierre published the original warp drive solution to Einstein's field equations. His calculations indicated that the amount of negative energy required would be comparable to the mass energy of a planet the size of Jupiter, on the order of 2 × 10 to the power of 27 kilograms converted into negative energy density. To be clear, this does not mean 2 × 10 to the power of 27 kilograms of ordinary matter. It means the equivalent mass energy of that amount, but with negative energy density, something never observed in macroscopic form. Years later, physicist Harold White at NASA proposed refinements to the geometry of the warp bubble. By altering its shape from a simple sphere to a toroidal configuration and adjusting the space-time distribution, his calculations suggested the required negative energy might be dramatically reduced, possibly to quantities on the order of kilograms rather than planetary mass. These proposed optimizations generated significant media attention and briefly created the impression that warp propulsion might move from theoretical impossibility to extreme engineering challenge. However, the underlying requirement remained unchanged: some form of stable, controllable negative energy density. And that is where the real barrier still stands. Subsequent analysis has been considerably less encouraging. The energy reductions proposed by White depend on specific assumptions about warp bubble geometry and the distribution of exotic matter that may not be realizable even in principle. More fundamentally, the requirement for exotic matter with negative energy density remains absolute and unchanged by any geometric optimization. There is no version of the Alcubierre drive that does not require this material, and this material has no known physical implementation, no quantum field theory mechanism that produces it in macroscopic quantities, and no experimental evidence for its existence anywhere in the universe. There are additional physical problems with the Alcubierre drive that go beyond the exotic matter requirement. The interior of the warp bubble, where the spacecraft sits, is causally disconnected from the bubble wall during travel. This means the occupants of the ship cannot send signals to the bubble wall to control it, and they cannot turn off the drive from inside. The warp bubble, once created, must be controlled entirely from outside, which creates an obvious operational paradox for a vessel traveling to a destination where no external controller exists. Some proposals involve pre-programming the bubble's behavior, but this requires that the space-time geometry of the entire journey be known and specified in advance to an accuracy that is not achievable for any real destination. The Alcubierre drive also produces extreme tidal forces at the bubble walls and concentrated high-energy particle radiation as interstellar hydrogen is swept up and compressed by the contracting spacetime ahead of the vessel. Calculations suggest that the radiation environment inside the warp bubble, generated by the accumulation and compression of interstellar particles during travel, would be lethal to any biological crew well before arrival at the destination. This is not a shielding problem that can be solved by putting more material around the crew compartment. It is a consequence of the geometry of the drive itself. The same space-time distortion that propels the ship also funnels deadly radiation into the crew space. Every proposed resolution of one Alcubierre drive problem introduces new problems of equal or greater severity. This is a pattern typical of mathematical constructs that are internally consistent within a limited formalism but disconnected from physical realizability. The drive works in the equations because the equations permit exotic matter as a formal parameter. Remove the parameter and replace it with the constraint that exotic matter does not exist, and the drive is simply not buildable. No amount of engineering sophistication can substitute a non-existent material with a known one. The Alcubierre drive is therefore not a technology that advanced civilizations are likely to have developed. It is not waiting behind a threshold of physical understanding that future science will cross. It is a description of what faster-than-light travel would look like if a material property that apparently does not exist were freely available. It is, in the language of physics, an existence proof conditional on an impossible premise. The condition is not met. The proof does not apply to the physical universe. Von Neumann probes and the entropy of self-replication. The self-replicating probe concept is the most seductive technical proposal for interstellar exploration, because it is the only one that appears to sidestep the civilizational lifespan problem entirely. Instead of requiring a civilization to commit resources for millennia to a single mission, a self-replicating probe, sometimes called a von Neumann probe, after the mathematician John von Neumann, who first formalized the concept of self-reproducing machines, uses the resources of each destination star system to build copies of itself. Those copies travel to nearby stars and repeat the process. The number of probes grows exponentially. Even at modest velocities, the wave of exploration could sweep across the entire galaxy in a few million years, cataloguing every star system without requiring any ongoing commitment from the originating civilization. The concept is named after von Neumann because he proved mathematically in the 1940s that a machine could in principle contain a complete description of itself and use that description, along with raw materials, to construct an exact copy. The proof was abstract and theoretical, a demonstration that self-reproduction was not logically prohibited, not a blueprint for an actual machine. The jump from von Neumann's abstract proof to a functional interstellar self-replicating spacecraft represents one of the largest engineering leaps ever casually assumed in discussions of alien technology. Consider what a functional von Neumann probe must actually do upon arriving at a new star system. It must first conduct a survey of the available resources, the compositions of asteroids, the properties of planetary bodies, the characteristics of the star itself. It must then design a mining and processing operation capable of extracting the specific materials needed for replication from the available raw materials, which will differ in composition from those at the origin system and from those at every subsequent system in the replication chain. It must build or carry manufacturing equipment capable of fabricating every component of its own structure: electronic, mechanical, optical, propulsive, from raw materials whose form and purity differ from anything it was originally designed to work with. It must assemble these components into a complete, functional copy of itself, including the full complexity of the original probe's design. It must then program the copy with the same replication instructions, launch it toward the next target, and either continue its own mission or prepare for deactivation. Each of these steps requires a level of autonomous manufacturing capability that does not currently exist and is not close to existing. The most sophisticated manufacturing robots in existence today operate within tightly controlled environments using precisely specified materials processed to narrow tolerances. They cannot adapt to arbitrary raw material compositions. They cannot design novel manufacturing processes on the fly. They cannot fabricate arbitrary components from first principles. The gap between current autonomous manufacturing and the capability required for a von Neumann probe is not a generational gap. It is a categorical gap that would require breakthroughs in artificial intelligence, material science, robotics, and process engineering whose nature and timeline are entirely unknown. Even assuming these capabilities could eventually be developed, self-replication introduces a failure mode that grows exponentially with the number of replication cycles. No copying process is perfect. Every generation of probes contains small errors, microscopic differences in component dimensions, slight variations in material composition, minor deviations in programming logic that accumulate across replication cycles. After many generations, probes may differ substantially from the original design, with accumulated errors in both hardware and software that degrade their capability, alter their behavior, or cause them to fail entirely. Natural selection of a sort operates on the probe population. Probes whose errors happen to improve replication, success will come to dominate the population, while probes optimized for scientific exploration may be outcompeted by probes that merely replicate more efficiently, losing the mission purpose entirely. This evolutionary drift is not an easily engineered away problem. It is a consequence of information theory and thermodynamics applied to copying processes. Any physical copying mechanism has finite fidelity. Finite fidelity means errors. Errors accumulate. Over hundreds or thousands of replication cycles across millions of years, the probe population evolves in unpredictable directions, driven by replication dynamics rather than by the original mission parameters. The probes spreading across the galaxy after 1 million years may bear little operational or functional resemblance to the probes that left the origin system. There is also the resource problem. A self-replicating probe arriving at a star system and consuming that system's raw materials for replication is engaging in an industrial operation on an astronomical scale, mining asteroids, processing ores, constructing spacecraft. This operation takes time, consumes energy, and changes the destination system in ways that may make it less useful for subsequent investigation by others, whether other probe generations or biological explorers arriving later. A galaxy filled with von Neumann probes that have been industrially mining every reachable star system for millions of years would look considerably different from a pristine galaxy. And notably, we do not observe any evidence of such industrial activity in our astronomical surveys of nearby star systems. The von Neumann probe concept is intellectually elegant and physically real in the sense that no fundamental law of physics prohibits it in the way that the speed of light prohibits faster than light travel. But it requires a level of autonomous engineering capability that is categorically beyond anything that exists or is on a clear developmental trajectory. It introduces exponential error accumulation that defeats the mission over long timescales, and it produces observational signatures that we would expect to see in the galaxy if any civilization had successfully deployed such probes on a galactic scale. We see none of those signatures. Kardashev scaling does not repeal relativistic physics. When the energy barriers to interstellar travel are laid out in quantitative detail, the quadrillions of joules needed for a small probe, the stellar-scale budgets required for a crewed mission, the most common response is to invoke the Kardashev scale. Nikolai Kardashev proposed his civilization classification system in 1964, describing civilizations by the total energy they command. Type 1 controlling planetary scale energy flows. Type 2 harnessing the full output of a star. Type 3 commanding the energy of an entire galaxy. The implication, usually unstated but clearly intended, is that civilizations higher on the Kardashev scale would find interstellar travel trivially affordable in energy terms, the way a modern industrial nation finds transcontinental shipping affordable despite its enormous absolute energy cost. This argument conflates two different things: the total energy available to a civilization and the minimum energy required to perform a specific physical task. These are not the same, and the distinction is critical to understanding why Kardashev scaling does not solve the interstellar travel problem. On the Nikolai Kardashev scale, a Type 2 civilization harnesses the full output of a Sun-like star such as the Sun, commanding roughly 4 times 10 to the power of 26 watts, or 4 times 10 to the power of 26 joules every second. That is an almost inconceivable level of power, exceeding the total energy produced by human civilization throughout its history in just a single second. By comparison, accelerating a 10,000 kilogram probe to 10% of the speed of light requires about 4.5 times 10 to the power of 18 joules, an amount such a stellar-scale civilization could generate in roughly 10 microseconds. In purely energetic terms, launching small interstellar probes at relativistic speeds would be trivially affordable for a Type 2 civilization. The energy budget itself would not be the limiting constraint. But everything else remains unchanged. The probe still takes 42 years to reach Alpha Centauri. It still faces the interstellar medium particle hazard at relativistic velocities. It still accumulates radiation damage throughout the journey. It still cannot communicate meaningfully with home while in transit. The navigation problem still requires the same precision. The arrival and deceleration still cost the same energy as the departure. The Lorentz factor still governs the relativistic dynamics. The second law of thermodynamics still applies to every component. Stellar scale energy abundance makes the energy cost affordable. It does not change anything else. Now scale the scenario to a crewed mission. A spacecraft capable of sustaining 100 people with full life support for a 42-year journey could easily mass several million kilograms at minimum. Accelerating such a vessel to 10% of the speed of light would require on the order of 4.5 times 10 to the power of 21 joules of energy, roughly 11 seconds of total stellar output for a Type II civilization as defined on the Nikolai Kardashev scale, assuming the energy of a star comparable to the Sun. In purely energetic terms, even a massive crewed interstellar mission remains affordable for such a civilization. But the energy budget does not remove the deeper constraints. The crew still ages 42 years in transit. The spacecraft must endure decades of micrometeoroid impacts, structural stress, and continuous exposure to interstellar radiation. Shielding requirements remain extreme. Navigational precision over light years must still be maintained. Communication delays stretch into years within a short time after departure and eventually become permanent. Every non-energy limitation, biological, material, relativistic and operational, continues to apply in full, scaling to a generation ship capable of carrying a self-sustaining population of 10,000 across a journey of 1,000 years to a star 100 light-years away, the kind of mission needed to reach destinations beyond the nearest few stars. The mass is in the billions of kilograms. The energy for acceleration and deceleration is in the range of 10 to the 25th power joules, and the Type II civilization is spending roughly 1 day of its total stellar output on a single mission. This is no longer trivial even for a stellar-scale civilization. It is a significant investment. And the ship still faces 1,000 years of operation in the interstellar environment with all the material, biological, social, and mechanical challenges that entails. More energy does not shorten the journey. It does not make materials more radiation resistant. It does not stabilize the society aboard the ship across 40 generations. Type III civilizations, commanding the energy output of an entire galaxy, can afford to launch far more missions simultaneously, thousands or millions of interstellar vessels at once, rather than the handful that would strain a Type II civilization's budget. But each individual mission still faces every constraint individually. 1 million ships crossing the galaxy still each take the same time. Each still faces the same hazards. The mathematics of the journey do not improve with the number of parallel attempts. A galaxy-scale energy budget expands the scope of what can be attempted. It does not change what happens to any individual attempt. There is also the question of whether Type II or Type III civilizations are physically achievable, rather than merely theoretically definable. A Type II civilization requires surrounding its star with a structure that captures most of the star's radiated output, a Dyson sphere or equivalent. The engineering, materials, and manufacturing capability required for a Dyson sphere are so far beyond current human capability that they cannot be meaningfully extrapolated from present trends. A Type III civilization harnessing galactic-scale energy would require restructuring the distribution of stars and their output across the galaxy in ways that are difficult to even describe physically, let alone engineer. These are not merely ambitious projects. They are projects whose feasibility has never been demonstrated even in principle for the materials and physics available in this universe. The Kardashev scale is a useful conceptual framework for thinking about the range of possible civilizations in the universe. It is not a solution to the physics of interstellar travel. Advanced civilizations pay the same physics bill as primitive ones. They can write a bigger check. The price does not change. The Fermi paradox is really a physics problem. In 1950, physicist Enrico Fermi sat down to lunch with colleagues at Los Alamos and asked a question that has never been satisfactorily answered. If the galaxy is old, if stars are common, if planets are common, and if even a small fraction of them produce intelligent life, then where is everybody? The universe should be teeming with civilizations. Some of them should be millions of years ahead of us technologically. Even spreading at a fraction of light speed, they should have colonized the entire galaxy many times over by now. And yet we see nothing. We hear nothing. No signals, no artifacts, no visitors, no unambiguous evidence of anything beyond our own civilization in the entire observable universe. Why? This is called the Fermi paradox, and it has generated an enormous literature of proposed solutions. The Great Filter, the Dark Forest hypothesis, the zoo hypothesis, the idea that civilizations inevitably destroy themselves, the idea that they transcend into forms we cannot detect, and dozens of others. Most of these proposed solutions are sociological or biological. They invoke things that might happen to civilizations to explain why we don't hear from them. But there is a simpler answer hiding in plain sight, one that does not require speculating about alien psychology or invoking catastrophes that might befall advanced societies. The Fermi paradox is not primarily a mystery about where civilizations are. It is a consequence of physics. If the analysis in the preceding chapters is correct, then interstellar travel at any significant scale is not merely difficult. It is, for all practical purposes, impossible for any civilization constrained by the laws of physics as we understand them. The speed of light cannot be exceeded. The energy costs of relativistic propulsion are set by physical constants that do not yield to engineering. The time required for interstellar journeys at achievable velocities exceeds civilizational lifespans for all but the nearest stars. Material degradation, radiation hazards, communication blackouts, ecological collapse, and social fragmentation combine to make long-duration interstellar missions profoundly unlikely to succeed, even if launched. These are not soft constraints that sophisticated civilizations have transcended. They are properties of the universe that apply to every civilization, everywhere, always. If this is true, then the silence of the cosmos is not paradoxical, it is expected. Civilizations do not visit us because civilizations cannot travel between stars at any meaningful rate. The galaxy is not full of visitors who have chosen not to announce themselves, or who are watching from a respectful distance, or who have destroyed themselves before reaching us. It is full of civilizations that are exactly where we are, marooned on their home worlds, or perhaps their nearest stellar neighbors, separated from everyone else by distances that the laws of physics have made effectively uncrossable. The zoo hypothesis, which proposes that advanced civilizations are deliberately avoiding contact with us, watching us the way wildlife biologists observe animals, choosing not to interfere, fails on exactly this ground. It requires that there be many advanced civilizations within reach of Earth who have both the capability and the coordinated will to maintain a galaxy-wide quarantine. If the physics of interstellar travel makes visiting us effectively impossible, the zoo hypothesis becomes unnecessary. The absence of visitors is explained not by their deliberate restraint, but by their physical inability to reach us. Occam's razor applies. The simpler explanation, grounded in known physics, is more compelling than the more elaborate explanation requiring coordinated alien sociology. The same applies to most other proposed solutions to the Fermi paradox that invoke civilizational behavior. The dark forest hypothesis, that civilizations hide from each other out of mutual fear, requires that civilizations could reach each other if they chose to, but choose not to. If the physics makes reaching each other impossible anyway, the hiding is unnecessary. The great filter arguments that some catastrophic step in the development of intelligent life or civilization reliably ends the trajectory before the civilization can spread, remain relevant as explanations for why civilizations are rare, but they are not needed to explain why civilizations don't visit. The physics already explains that. What the Fermi paradox, reframed as a physics problem, tells us is that the universe is structured in a way that produces a galaxy of isolated civilizations, each burning briefly and brilliantly in its own corner of the cosmos, unable to meet its neighbors, not because of intent or accident, but because of the architecture of space-time itself. The silence is not the sound of empty space. It is the sound of a universe that places its inhabitants far apart and gives them no fast way to close the distance. Interstellar isolation under relativistic constraints. The laws of physics were not written to be kind to the ambitions of intelligent life. They do not care that civilizations develop curiosity or build technology or look upward and wonder. The speed of light was set before any mind existed to measure it. The energy costs of relativistic travel were fixed before the first star formed. The passage of time, relentless and universal, was flowing long before biology invented consciousness to notice it. These constraints do not discriminate. They apply to every particle, every wave, every ship, and every civilization anywhere in the cosmos, without exception. What this analysis has built, chapter by chapter, is not a pessimistic argument. It is an honest one. The distance between stars is real. The energy required to cross it is real. The degradation of materials, the fragmentation of societies, the entropy of all organized systems, all of it is real, measurable, and grounded in the most tested theories in the history of science. This is not a case of human imagination failing to grasp what future technology might achieve. It is a case of physics setting terms that no amount of imagination changes. If intelligent life exists elsewhere in the galaxy, and there is every reason to think it might, then the most probable picture is one of profound, permanent isolation. Civilizations separated by light years of void, each capable of looking outward and seeing stars, each capable of wondering about what might orbit them, and none capable of crossing the distance in any time that the civilization or its mission can survive. The galaxy is not a neighborhood. It is an archipelago of islands so remote from each other that the ocean between them has never been crossed, and under the laws of this universe may never be. This should not diminish the wonder. A universe that contains even the possibility of intelligent life on billions of worlds, each one alone with its own sky, its own questions, its own brief and extraordinary existence, is a universe of staggering richness. The fact that we cannot meet does not make the others less real. It makes the silence around us more meaningful. We are here against enormous odds, asking questions that the universe itself seems designed to keep unanswered. That perhaps is the most remarkable thing of all.